We're looking forward to our meeting with you all tonight. So first, in terms of announcements, Doris said she had a couple of announcements. So you want to get up or you want me to bring the mics over to you? Okay. We can do that.
Thanks. Is it on? Well, I have a loud enough voice. I don't need the mic. Recording it. Oh, they're recording. All right. First of all, I have greetings from Ray Sullivan. I talked to him yesterday, and he wanted to have me tell you all that he's doing okay, holding his own, not in too much pain, and coping very nicely. He sounded awfully good. He actually sounded cheerful, and it was wonderful, wonderful to talk to him. He's not able to travel much, so otherwise he would have been here this evening, but he wanted you all to know that he sends his greetings. The second thing, for any of you who haven't heard, there's a possible eruption in Iceland imminent. The news is very interesting. It's a rift that's part of the same system as the eruptions of the last several years. It's parallel to the last two, but further west, which had, and unfortunately, under one of the Grindavik, one of the lovely fishing villages on the south shore. So it's being taken very seriously. The other two, as you will remember, out in the country, the lava filled a couple of valleys that were not populated. But this, if it erupts, it's a 15-kilometer fissure, extends out into the sea a couple of kilometers, and it has the potential for doing a great deal of damage. It's already damaged the town of Grindavik, and they're which has been evacuated, and they're worried about the potential of a subsea eruption that would send a lot of stuff in the atmosphere. So if you want to follow it, Googling the eruption in Iceland will get you a lot of links. The official Iceland news link is the Icelandic Meteorological Institute, and that the link is ruv.is. And there's lots of news and lots of blogs. It's very, very interesting and very serious. Oh, yeah. Yeah, John, I've been in touch every couple of times a week with my friend of now 15 years who guided all the trips I did there, Elizabeth Brand. She lives about 30 kilometers from Grindavik, and her apartment, she says, the dishes are rattling all the time. They've had 30 or 40,000 earthquakes in the last 2 weeks, almost all of them small. I mean, they're counting everything magnitude 1 and up, Richter 1 and up. And there have been 200 or 300, they're magnitude 4, a few 5, and that's enough to do some damage. The houses have a lot of plaster cracking, and the streets are, and of course Iceland is spreading apart. It's a rift. It's a spreading plate boundary. You don't read about that on these blogs, but we know it is. And so there are cracks and the ground is spreading. The pictures are pretty astounding, but Elizabeth says it's hard to get any sleep because everything is rattling all the time. And she uses language about this one that I've not heard from her in all these years, about how it's really terrible and terrifying, and instead of how interesting and so on. So it's more serious to them than the past. But ruv.is will do it. Thanks.
Thank you.
Yeah, that's what they're afraid of is this surge or Westman Island.
Okay, very good. Thank you. And following up on Doris's comment, if you haven't seen the newsletter for this month yet in detail, there's a nice article in there about Ray's presentation that took place at the September meeting. So we really appreciated getting that from was it John that put that together? I forget. Where's Mark Sorensen? Who's the? You remember? Oh, okay. I look forward to it. Thank you. Okay, other announcements. Will, anything about field trips or Phil? Come on up. Yeah.
Thanks largely to Greg, we've been organizing a pre-trip for Angel Island. The idea is to have a series, probably multiple NCGS trips to Angel Island sometime in the spring. But this little gathering of a few people has started like being a magnet for all sorts of people. It's going to be almost a Penrose conference, sort of like 24 experts all gathering and probably arguing with each other, but should be great fun anyway, as long as it doesn't pour down rain on the 9th of December. Thanks for doing all the logistics on that.
Thank you. Okay, Phil, come on up.
As you know, the NCGS, we have our Richard Chambers Memorial Scholarship. Applications are due on December 2nd. I have a few inquiries from students around Northern California. I don't know whether we get one applicant or 20 until my mailbox fills up. I hope once I get them that I'll have a number of the members of the NCGS or officers in that help me evaluate them and make a decision on who gets the scholarship. So
good. Thank you. And the board did approve an increase this year, so we're actually giving out $4,000 to various students, which is great. So, okay, let's see. My other usual suspects. Don Medvedev, do you have anything? No? Okay. Anybody else? All right. With that, then I'm going to turn the floor over to Greg Bartow, who's our program director tonight, for introductions.
Hey, good evening, everybody. So before I introduce Jeff, I just want to talk about the next meeting. Won't be until January. So the January 31st meeting will be Pallav Sarma, Physics of Embedded Machine Learning for Modeling and Optimization of Mature Oil Reservoirs. So be an interesting technical talk there. And so it's my pleasure to introduce Jeff Unruh. He's speaking on the Seismic Hazards Evaluation of the Midland and West Tracy Faults near Byron, California for water infrastructure projects. Jeff has been very good with his time to NCGS. He was one of the co-editors and provided a paper in the GSA memoir on Mount Diablo. He's been a speaker in the past. He contributed to the Geology of Mount Diablo guide. It's great to have you here. Let me just tell you a little bit about Jeff. So Dr. Unruh is the president of Lettuce Consultants International and a certified engineering geologist with over 30 years of experience in neotectonics, structural geology, and seismic hazards evaluation. He's managed numerous large multidisciplinary investigations for dams, LNG facilities, nuclear power plants, and military installations. Recent projects include seismic hazards analysis for the design of the new Sites Dam and Reservoir in Northern California, and neotectonic studies for nuclear facilities in the West. Dr. Unruh currently is the manager and technical lead on a project to develop a probabilistic subsidence forecast for the subsidence of the California Aqueduct in the Central Valley. He's in addition to his considerable professional consulting work, he's an active member of the scientific and research communities. He's held a courtesy position as a research geologist at UC Davis and is a GSA fellow. Dr. Unruh is currently an adjunct faculty to Diablo Valley College, where he teaches a class on California geology, which I would like to take that class. That sounds great. So with that, let's welcome Jeff Unruh. Thank you, Jeff.
Well, thanks, everybody. Go backwards a little bit. So what I'd like to talk about is some seismic hazard evaluation of the Delta, and I'm going to focus specifically on the characterizing the Midland and West Tracy faults as seismic sources. But the context of this, I'm going to get into just a little bit in the course of this talk, is what the unique seismic hazards in the Sacramento-San Joaquin Delta are. And I'll also talk about kind of the modern state of practice for seismic hazard evaluation, which this is a probabilistic seismic hazard analysis. And in order to do this, the key pieces of information that we need are, first of all, where earthquakes occur, where are the active faults, how big of an earthquake do these faults generate, and how frequently do the faults produce earthquakes. So the idea is to generate a model of the sources of all of these earthquakes, their occurrence and everything, and put them into a probabilistic model. And then we can start asking some interesting engineering questions. And I'll talk about that as we go along. Well, oh yeah. I don't think it liked that. Okay, wait a minute. All right. So just to start with, everybody here knows that we're sitting on a plate boundary on the east side of the Pacific Plate. Pacific Plate's moving about 48 millimeters per year to, okay. About 48 millimeters per year to the northwest with respect to, point in Kansas, stable North America. About 75% of that motion goes up along the west side of California. The other 25% branches off the Pacific North American plate boundary down here in the Salton Sea, goes up along the east side of the Sierra Nevada and splays into the Basin Range. And what that does is it breaks off a large chunk of California and entrains it in this motion parallel to the Pacific Plate. So you can see that in this map here. This is a map of the GPS velocity field. All these vectors are the motions of GPS stations in terms of millimeters per year, the velocities of them with respect to North America. And so you can see that all of the plate motion is not localized along in Western California. The Sierra Nevada and Central Valley are moving together as a rigid block, about 12 millimeters per year. And what you can see in this image is that this is the motion of the Pacific Plate here. You can see that the Sierran microplate is moving a little more to the west on the average with respect to North America than the Pacific Plate. And can show that maybe in a little more of a schematic way here in this next image. So actually the Sierran microplate, this piece of California that's moving, with respect to North America, is actually moving as if it's rotating counterclockwise about a point out here in the Southwest Pacific. So what that means is that instead of just moving parallel to the Pacific Plate, there's this component of convergence between along our plate boundary, the Pacific Sierran plate boundary that we live on. And that oblique convergence is accommodated by mixed strike slip and thrust faulting in the coast ranges and across the Pacific Sierran plate boundary. Okay, so that's the general setting for what's driving the earthquakes in Western California. What I want to do now is look in particular at the tectonic activity on the very kind of the Sierran side of this plate boundary here in the Delta. So this is the San Andreas Fault runs up and through here. The Calaveras Fault is here. Here's the Hayward Fault, the Northern Calaveras Fault. And by the time you get out to the east side of this plate boundary, you're down to a very small residual amount of motion, but it's not zero. Okay, so there are faults, I'm going to talk about them in a minute, that go along the west side of the Central Valley and that are in close proximity to the Delta. But all of the tectonic activity in this part of Western California, all these active faults generate earthquakes that are potentially felt out here in the Delta. Okay, so let's take a look. Let's zoom in and take a look at the area around the Delta a little bit. So this is a kind of a classic view of the Delta. Pittsburgh and Antioch and Brentwood are out here. Rio Vista's up here. And the Delta is where the San Joaquin River and the Sacramento River come in out of the Central Valley. And the confluence is here, passes through Suisun Bay, Carquinez Strait, goes out to the San Francisco Bay. And there are tributary streams to the Sacramento and San Joaquin River, and they all pass around these isolated tracts of land called islands. And so and there's a lot of agriculture in these islands. Now, none of what you're seeing here is a very natural, is part of the natural landscape. This has all been heavily modified by people over the past 150 years or so. And here's a reconstruction of what this area looked like prior to it being drained and brought into agriculture. Okay, so the upper slide is the kind of a view to the north from the San Joaquin Valley looking up toward the Delta. So here's the Montezuma Hills and Rio Vista's over here. Brentwood would be over here, and Pittsburgh and Antioch would be over here. This is again, all the little tributary streams going around these tracts of land, these islands. But this is what it looked like back in the middle 19th century. It was a big inland marsh, and there were, aside from perhaps the San Joaquin River, most of the streams that were flowing through here were not within fixed channels, migrated around within this wetland area. So in order to get from here to here and bring this land into agriculture, this is what was done. The existing channels that were flowing through the Delta were bounded by natural levees. So what folks did was they dredged or found fill material and piled it up on top of the natural levees to build them up. And then they drained the intervening areas. This is what we now know of as the islands, to expose this nice peat soil. This peat soil is it's very fertile. It's great for growing fruit trees. If you've been there in the Delta, you've seen the pears and so on. But what happens when you expose the peat soils, which accumulated in anoxic conditions, to sunlight and oxygen, is they get attacked by microbes and they get oxidized, and they basically turn into dust and blow away. And so the surface of the Delta Islands progressively subsides and sinks until it's well below the average elevation of the water in the channels. And I'll add that the water in these channels is all graded to Suisun Bay and then out through Carquinez Strait and out to the San Francisco Bay. So basically these are all graded to sea level. So these channels are just barely above sea level, which means that these Delta Islands, for the most part, are below sea level. And what happens is when these levees fail, the water just floods in and fills up these islands and these tracts. So these islands are actually something, calling them an island is something of a misnomer. When you think of an island, it's something that sticks up above the water in the ocean or something like that. These are actually areas that are subsided below the average elevation of the water around them. And in fact, they're below, the average elevation is below sea level. And that's what this map is showing you right here. This is just if we took all of the water and out of the Delta, or if we just measured the average elevations of the bottoms of these tracts of land, a lot of this area, almost everything in this blue area is below sea level, if all of this stuff is below sea level. Now, this is important because even though this is below sea level, water is not intruding in here from the San Francisco Bay because of the flow of fresh water through these little sloughs and everything, and that flow of fresh water is protected and guided by these levees that have been built up around it. These levees are not engineered structures. Again, most of them were built back in the late 19th century, maybe early 20th century, and they were just created by just dumping fill on top of the natural levees. So they're not made to withstand strong ground shaking. And in fact, some of them have been tested and they're quite susceptible to liquefaction, like Jello. So the concern is that what if we have a big earthquake in the either within the delta or a very large earthquake on a fault that's outside the delta, but it's still capable of generating ground shaking that's strong enough to possibly knock down these levees. Well, the problem is that if a lot of these levees failed, the water would come in. In fact, my slides are a little out of order. Maybe I should just show you this. The concern is that if you get a substantial earthquake, it'll knock these levees down. And all these holes will basically fill up by drawing salt water in from San Francisco Bay. And this is an interesting, a good slide to point this out. This is the direction that the salt water would come in. This is Clifton Court Forebay down here. This is the point that water is stored after it's passed through the delta in order to pump into the California Aqueduct and the Delta Mendota Canal, which is the state and federal water transportation conveyance down to the San Joaquin Valley in Southern California. So if this fresh water, if the salt water comes in here and it'll from a massive levee failure, the concern is that it'll get pulled down into here and affect the quality of water that goes south to the to Southern California. Let me back up. Okay, and in particular, for example, this is a graphic from Metropolitan Water District in Southern California. There, the pathway for the fresh water that comes through the delta that ends up in Clifton Court Forebay and gets pumped into the California Aqueduct and Delta Mendota Canal is kind of right through here. It's right through the area that's essentially below sea level. So again, the pathway for the fresh water that ag and municipal users down in Southern California depend on is right through here, right through this area of subsided delta quote islands unquote. Yeah. Well, they're they were natural ephemeral streams that were confined by these levees and eventually turned into permanent channels, quasi-permanent channels. Yes, thank you for pointing that out. Yeah, the pumping of the water through the delta actually does pull it down uphill a bit. It's not truly uphill. It's still going downhill, but it's in the opposite gradient that the water normally goes out the valley. Yes. Oh yes, I'm sorry.
My question is this also the area where they're talking about the tunnels?
Yes. The question is this the area that's being talked about for the construction of the Delta conveyance tunnels? And the answer is yes. And the Delta conveyance tunnels are an attempt to engineer this problem. Or it's an engineering a way of addressing. It's an engineering solution to the problem of the fragility of the Delta levees. And the idea would be building a tunnel that starts up here in the northern part of the Delta, goes through the Delta, and the southern end of it would be down into here somewhere. That's still a work in progress, exactly where the southern portal of the tunnel would be, and also whether it would empty into the existing this is Clifton Court forebay, or whether this forebay would be expanded into another, it would be a different structure or a larger version of that structure. But yeah, that's the Delta Conveyance Tunnel is a solution for the partly a solution for the fragility of the levees and the potential impact of disrupting the flow of water through the delta. Any other questions about this before we? Yes. Well, in an extreme example, yeah, it would, the quality of it would be impossible to prevent the eastward flow of salt water from the bay. Basically, that water would come in to fill up this hole. And it would, I don't know how long it would take, what it would take to clean that up. Want to speak to that, Ken?
I was just gonna say, depends. Studies from my understanding. Oh, I'm sorry.
Yeah.
It just depends on how much of the levees fail, because if you think it's really about displacing the volume of water that's salty, and you have to then dilute that back down to a usable water supply level. And that could take up to, I've heard, 2 or 3 years. So if you could think about Los Angeles not having water for 2 or 3 years, well, they have water from other sources, but they'd be thirsty. They wouldn't have a lot of stuff. Anyways, sorry.
Well, there's the cities in Southern California, there's the agriculture users in the San Joaquin Valley. The state directs some of that water out to the coast, the Central Coast. So this water goes to a lot of places from the Delta. Okay, so to address this problem, a number of studies have been done going almost 20 years ago now. The state of California Department of Water Resources did a study to try to evaluate what the potential is for an earthquake causing a multi-levee failure, or a widespread collapse of the levees that would change the hydrology in the Delta. And so what they did was they considered they did a probabilistic analysis to look at the not only earthquake sources within the Delta that could cause strong ground shaking in the Delta and liquefaction of levees, but also earthquakes that occur on some of these faults out here in the East Bay and even extending out to the San Andreas Fault, going up the peninsula. These, even though these are farther away, some of the earthquakes that are on these faults are larger possibly than the earthquakes that could occur in the Delta. And so depending on the size of these earthquakes and how much the shaking is attenuated between the faults and the Delta, they could contribute to some of the collapse of the levees. So the idea was to put all this into a probabilistic model. And in a probabilistic model, you consider all of the potential sources of ground shaking that could affect a site. You consider how frequently those earthquakes can occur, given the size of the earthquake and the distance of the earthquake from the source, how much the shaking energy is attenuated at the site. And you can put all this into a probabilistic model and convolve it to ask this specific question up here. What is the probability that the level or intensity of ground shaking at over a specific duration of time will exceed a certain level? So in the Delta, that would be, for example, what's the likelihood that the ground shaking could be sufficient to knock down 20 levees over the next 100 years? What's the probability of that happening? You can ask that kind of question with a probabilistic analysis. And they did that. And in the outcome of the DREAM study, the Delta Risk Management Strategy study, was that they looked at the possibility of one of these large earthquake events, knocking down multiple levees over a 25-year period. What they found is that given the fragility of the levees, the frequency of earthquakes, the intensity of the ground shaking, that there's a possibility that upwards of 20 to 30 levees could be knocked down. The probability of that happening over a 25-year period is about 40%, given the state of knowledge about the earthquake sources and the levee fragility at the time. So we're coming up on the 25th forecast window from the Dreams event. But what this forecast is also saying is that, you know, over a period of maybe about 70 years, the probability of something like this happening is getting close to about 100%. So the purpose of a lot of the work that we've been doing is to try to revise and reduce the uncertainty of the frequency, magnitude of earthquakes on faults in the Delta and outside the Delta, to try to improve this type of a model so that you can ask better informed engineering questions about the fragility of the levees and the likelihood of these kinds of catastrophic events. Okay, so with that as a backdrop, I want to show you some of the work that we've done to try to improve the seismic source characterization of two major faults in the Delta, the Midland and the West Tracy Fault. Okay, so the Midland and the West Tracy Faults are the faults that are the known active faults that are sitting pretty much right in or right directly adjacent to the Delta. The Midland Fault runs right up in through here like so. It's on the west side of the Montezuma Hills. And the West Tracy Fault is down here, pretty much between the town of Tracy and extending up toward the town of Byron. Okay, so first I'm going to talk about the Midland Fault, because I won't dwell on it too much because I talked about it in other presentations, but I want to show you, I'm going to spend a little more time on the West Tracy Fault to show you some new data that have been acquired to try to characterize this fault, both as a seismic source and as a ground deformation. Okay, so the Midland Fault. Well, okay, let me just, this is a little better map or a little less crowded map, I might say. The Delta, here's the Delta region, here's the Midland Fault, okay, and here's the West Tracy Fault down here. Now, the Midland Fault is originally was a west side down normal fault in early tertiary time, and it bounded the western side of a graben that formed within the ancestral Western California Forearc region. So the Midland Fault was the eastern boundary fault of this graben, and the Kirby Hills Fault was the western boundary fault of this graben. And let me see, I forget what the next slide is. Oh, okay, so this is just this is a map just showing you kind of the graben that was bounded by these faults is the Rio Vista Basin. And the Midland Fault is, we've mainly focused on the southern part of the Midland Fault, but the Midland Fault is considered, at least by some people, to continue up north of Rio Vista and the Montezuma Hills as part of a series of right stepping on echelon splays that head up toward Liberty Slough and some of the gas fields in the Delta up in this region up and through here. Okay, so this is kind of I'll show you a classic AAPG cross-section across the Rio Vista Basin and these structures in through here. Okay, so this is the Pasquini and Milligan 1967 section. So this is west over here, east over here. Here's the Midland Fault, and here's the Kirby Hills Fault. And if you look within the section, what you can see is the growth of the Paleogene section, the thickening of the Paleogene section on the west side of the Midland Fault relative to the east side of the Midland Fault. So there's a lot of growth in the Paleogene section, and then on the Midland Fault, and then it pretty much dies out up into the Oligocene, the Markley Gorge up into here. Okay, so that west down early tertiary motion is very well understood and very well documented in the study of the Rio Vista Basin for all the gas that was produced in here. But what's interesting is if you look at this basal Miocene unconformity, it's actually, there's structural relief on it. It's bumped up over in the hanging wall of the Midland Fault. And what this suggests is that the Midland Fault was reactivated post this Miocene unconformity in a reverse sense. And there's, let me show you a seismic reflection profile. Yeah, this is a seismic reflection line I stole off of the internet. I can't remember exactly where it came from, but yeah, no, I believe it. And this is west over here, and this is east over here. Here's the Midland Fault. You can see who the person who prepared this interpreted the top of the Damangene and the Hamilton Sand. So you can see the growth of the early tertiary section into here, and the west side down displacement of the Damangene. But if you follow the up here in the upper part of the section, there's this unconformity here in the shallow part of the section is uplifted and tilted to the east. It's been folded by reverse displacement on the Midland Fault. There are other seismic lines that I've seen that show the same relationship. So this is I was doing some work with a couple colleagues of mine, Scott Hector and Karen Blake, who both are gas exploration geologists, and they know they've worked the Delta. And what we did was let me just go back. What we did was we got the well data from this area and tried to repick this basal Miocene unconformity and then contour it and map it out in the Delta. And this is an example of picking that unconformity on some of the e-logs from the wells on an east-west line through the Delta. But basically what we found is that there's about 200 meters of west side up relief on this basal Miocene unconformity in the Delta. And we mapped this, we developed a structure contour map of this unconformity. So all these yellow dots are the wells that we use, as well as pics or elevations of the base of the Miocene from the outcrop belt. And basically here's the Midland Fault, and there's positive, again, about 200 meters of positive structural relief on that unconformity over the Midland Fault. So using that information, before I jump, let me just go back. So there's, pardon me for, you can tell I've very well practiced on these slides. I know what's coming next. So I'm also well practiced on using this. Okay, so here's the Midland Fault. What we see is west side up structural relief or a fold relief on this Miocene unconformity. There's some recent earthquake activity in the Delta that also gives some indication what the kinematics might be of this fault. So some of you, maybe a lot of you are aware that in back about a month ago, there was a moderate magnitude earthquake in the Delta, magnitude 4.2 earthquake. The epicenter is located out near Ileton, roughly, and this is just a map showing the epicentral location and some of the felt effects in the area around the Delta. This is zooming in a little bit. The epicenter of that 4.2 earthquake is right there. Okay, so the trace of the Midland Fault, I didn't draw it in on this map because I stole this map off from the USGS website, but the Midland Fault runs right into here like so. So the epicenter of this earthquake is just a little bit to the east of the Midland Fault. And it occurred around 6 or 8 kilometers depth, so that would probably be in the footwall of the Midland Fault. But there was a moment tensor solution for this earthquake. Now, what this looks like, you might be familiar with beach ball representations of earthquake displacements. This is a moment tensor. It's not quite the same thing as a focal mechanism. A focal mechanism is modeling the earthquake as a discrete slip on a fault. What the moment tensor is a 3D representation of how the energy radiated away from the source of the earthquake. So if there's complications about how the fault ruptured during the earthquake, if instead of just sliding back and forth, instead that one of the blocks rotated, for example, relative to the other. Or if there are other faults that broke as part of the earthquake sequence, that information is kind of captured in the energy radiation pattern. So what this looks a lot like a beach ball, but you'll notice that it doesn't quite close up and form a perfect beach ball. That's because there's some complications to this earthquake. But what this is telling you is that the moment tensor is saying that most of that earthquake was primarily a right lateral strike slip event. There was the fact that this blue field kind of bleeds over suggests that in addition to right lateral motion, there was also a component of crustal shortening that was taken up by this event. Okay, so this is the magnitude 4.2 event. There was a couple of other earthquakes that occurred in and around that magnitude 4 event within about a week or so. So here's that magnitude 4.2 event. This blue dot here is a smaller earthquake and nearly a magnitude 3 that occurred about 5 days later. And this event has a nice clean focal mechanism, a nice clean beach ball diagram. And what I think is well, let me just back up again. So first of all, this smaller event, this blue dot, is almost smack on the Midland Fault. The focal mechanism, which is representing the earthquake as a simple shear dislocation on a single fault surface, shows that this nodal plane of the focal mechanism is pretty much parallel to the Midland Fault. It's dipping steeply to the west. Midland Fault dips to the west, and it's dominantly a right lateral strike slip focal mechanism. So at least in terms of these small events out here, there's some indication that in addition to the reverse displacement that we see on that fault expressed in the seismic sections, that kinematically there might be a component of right lateral, a fairly substantial component of right lateral slip occurring on this fault. So just to sum this stuff up, the Southern Midland Fault formed as a Paleogene normal fault along the eastern margin of ancestral Rio Vista Basin. It's been reactivated as a reverse, or what I think is very likely a reverse oblique fault in late Cenozoic time. Given 213 meters of west side up late Cenozoic structural relief, probably occurring in about the past 5 million years or so, what that gives us is an estimate for the reverse slip on the fault on the order of very low tenths of millimeters per year, maybe to hundreds of millimeters per year. That's just the reverse component. If there's a right lateral component that we can't see, that would increase the slip rate. But the slip rate on this fault is probably in the very low tenths of millimeters per year at the high end of its slip rate. The fault's 32 kilometers long. So given the dimensions of the fault, earthquake magnitudes are scaled to fault dimensions. Given the length of the fault, it's likely down dip geometry and width. It's probably got enough potential rupture area to generate a magnitude 6.5 to 6 3/4 earthquake. That's just if this fault breaks all by itself. The U.S. Geological Survey believes that the Southern Midland Fault may be connected to the West Tracy Fault, which we're going to talk about next, and that the two faults may rupture together in a single earthquake, in which case that's a much larger magnitude if both of those faults break at the same time. Okay, so any questions about this before we go on to the West Tracy Fault? All right, so that's the Midland Fault. Again, about a magnitude 6.5 or 6 3/4 earthquake source with a very low slip rate in along the western margin, or pardon me, the eastern edge of the Montezuma Hills. Okay, the West Tracy Fault is located down here. It's between roughly between the town of Tracy and up here near the town of Byron. It strikes northwest, southeast, and dips to the southwest. In contrast to the general northerly strike of the Midland Fault. But this structure is down here, and it passes through or beneath Clifton Court Forebay, that reservoir that that's kind of the launching pad for the water that eventually goes into the California Aqueduct and the Delta Mendota Canal. So let's take a look at the West Tracy Fault. Well, first of all, about 20 years ago, maybe even longer, I was corresponding with a gas exploration geologist named Rob Sterling, who was working in this area. And Rob gave me a bootleg seismic reflection profile across the West Tracy Fault that probably is located somewhere down into here. So I'm going to show you that seismic line. Okay, so like everything you get from the oil industry, the vertical scales cut off. I'm assuming this is in time, but you never can tell. There's no shot points, but I know this is west. I know this is east. And so here is the West Tracy Fault. Okay, so there's a well-expressed East Virgin or probably Northeast Virgin fault propagation fold, a monocline in the hanging wall of this fault. And what you can see is that if you trace, you can see the truncation of these reflectors down here that Rob is, by the way, this is Rob's interpretation. I didn't get an uninterpreted version of this profile. This has got Rob Sterling's interpretation on it, but he's drawn the West Tracy Fault along the truncations of these reflectors down through here. And you can, if you look closely, you can see that these reflectors carry through. They're not really offset. So these are probably folded rather than faulted. So the fault's blind. It tips out somewhere down into here. And what you can see is a couple other interesting things. You can see this nice fault propagation fold up into here. And then there's an unconformity in the shallow part of the section. And the unconformity is deformed. It's uplifted and tilted to the east, but it's not folded in exactly the same way as a steeper section. So the early growth on this fold produced this nice monocline, this fault propagation fold. The late deformation has probably been more driven by fold or accommodated by fold limb rotation. But basically, the West Tracy Fault is this blind fault underneath this fold along the west side of the valley, and it has deformed the shallow part of the section. Exactly what those units are, I don't know. Rob has interpreted this contact here, this unconformity, as the Cretaceous Miocene unconformity. I don't think that's right. I think this is probably older, maybe Eocene, based on the section that we see up farther to the north. The Miocene is probably up into here somewhere, but this probably is Pliopleistocene up into here. So there's late Cenozoic, post-Pliopleistocene slip on this fault. Okay, so as I said, the fault kind of trends along the west side of the valley, dips to the southwest underneath the range here, and it projects right underneath Clifton Court Forebay. Okay? So the state of California was interested in this fault because of their facilities here, Clifton Court Forebay, and the intake for the intake channel that leads up to Bethany Reservoir that then puts water into the California Aqueduct. So they acquired a lot of legacy seismic reflection lines in this area from a broker, reprocessed them to see what the West Tracy Fault looks like underneath Clifton Court Forebay. And this is an example of one of the seismic lines from that goes from southwest to northeast along the margin of Clifton Court Forebay. Again, what you can see, this nice flat section out here in the valley, more or less flat, but then there's this poorly imaged, but still can see it's a monoclinal fold in the hanging wall of where the West Tracy Fault is, probably somewhere down into here. What else you can see in here is it's kind of interesting. You can see that these beds come up and appear to be truncated against what look like they're probably flatlying reflectors here. And so this is just to highlight some of the reflectors. And if I was doing this interpretation, I think I would put the West Tracy Fault a little over here rather than here, but you get the general idea is that the West Tracy Fault is underneath Clifton Court Forebay, and there's been uplift and folding in the hanging wall of the West Tracy Fault that affects these very shallow reflectors in this section. Okay, well, to follow up on the study, this review of the older reflection data was done probably back in the late 1990s, early 2000s. And so about 20 years later, DWR got interested in looking at a surface lineament that's along the trend of the West Tracy Fault and present up here to the northwest of Clifton Court Forebay. So the next slide I'm going to show you is going to be a Google Earth image of this area right through here, where we can see this this lineament along the fault. Okay, so this is Byron Highway here. The town of Byron is here. Clifton Court Forebay is just off the edge of this this image down here. And this lineament I want to draw your attention to is this feature right in through here. This is along the trend of the West Tracy Fault, this lineament right in through here. What this is an area of older uplifted alluvial fan deposits that are surrounded by older, or I should say they're surrounded by marshier deposits that were actually close to tide level or tide line back in the early and middle part of the 20th century. So this lineament right in through here is associated with a up on the west break in slope. And let me show you this is a topographic profile, very vertically exaggerated across that lineament. So southwest over here, northeast over here, you can see the land surface is about 3 meters higher on the west side of this lineament. And that I want you to keep the shape of the land surface in mind, because there's two hypotheses that we can entertain. One is that what we're looking at here is the surface expression. What this could be is a fault scarp. It's a place where the fault is actually ruptured up to the surface and uplifted the land surface, and the fault actually breaks the surface right here. The other alternative hypothesis is that what we're looking at is a fold scarp. It's a place where incremental uplift and folding has occurred as a consequence of the last earthquake or couple of earthquakes on the fault. So to address that, DWR acquired a new seismic reflection profile across this lineament. So this map shows where the location of the reflection profile was acquired. So DWR had access to this property that belongs to an elderly woman named Mrs. Perry. And Mrs. Perry granted permission to shoot a seismic line through there. Her property ends at Byron Highway. There's property over here on the opposite side, west side of Byron Highway, that has an orchard in it. And what we dearly wanted to do was shoot the seismic line across Byron Highway, all the way across this unconformity at the base of the Pleistocene Tulare Formation, where it sits on top of the Neroli Formation, because we wanted to use this as a marker projected in the subsurface and use it to measure structural relief on the Pleistocene. And there was a lot of negotiations with the owner of this property, who has an olive orchard here. We got very close to getting permission to shoot the seismic line on the land. We even identified a vibroseis that has a nice narrow track that we could fit up between the trees, but we couldn't just make the timing work. The property owner did not want us in here during certain times of the year when they were doing harvesting and such. So we just had to take what we could get, and we shot the seismic line on Mrs. Perry's property right up to the edge of Byron Highway. And I'll show you why it would have been really nice to have this extra bit of seismic line when I show you what we found. So anyway, shot the seismic line along this northwest southeast trend across the Perry property. Here's out in the field with the vibroseis. The view is off to the west. Byron Highway's at the foot of the hills here. You see that green area? That's the orchard that we wanted to shoot up into, but we couldn't make it work. Okay, so this is what the seismic line looks like from Mrs. Perry's property. It was when we acquired it, there was a very narrow source receiver spacings to get a lot. We wanted to get really sharp imaging of the shallow part of the seismic, shallow part of the stratigraphic section. This is a post-tack time migrate section that's just had the vertical scale stretched using the velocity model to kind of approximate what the vertical depth is. So this gives us this is a pretty good image to take a look at the stratigraphy up here. But to work with the structure, we had a pre-stack depth migrated section developed. And that's what this section is here. So there's less detail in the shallow part of the section, but we think that the geometry of the deeper structure is probably better represented. Okay, so this is looking at this. My initial thought is that the West Tracy Fault is somewhere in here. There's folding. Maybe it extends as far up into the section, but you can trace a lot of reflectors through this synformal hinge. And certainly as you get up in the shallow part of the section, that indicates that the fault really does not rupture up to the surface. This is a highly exaggerated topographic profile. So you can see though that the synformal hinge projects right up to that escarpment, that geomorphic feature that we were looking at. Okay, so this is what the seismic line looks like, and this is how we projected the outcrop data in on the west side of Byron Highway, where we could not shoot the data, and what we suspected is that this was not just an unconformity, it was an angular unconformity, and we really wanted to be able to accurately carry the folded stratigraphy into the subsurface. So we have a few strikes and dips, and we have the classic Eocene section at Cape, Damangene, and Nortonville here. We can carry that through, and this well that's on the Perry property, the Sproul well, goes down to and hits the top of the Damangene. So this interpretation of the reflection data and how it's married to the outcrop data is at least partially constrained by some well data. But this is how we think that the rest of the structure and the stratigraphy project into the seismic line. And as my friend Randy, who worked with, who did supervise the field acquisition, every now and then when I talked to him, he said, "Jeff, you should have had him shoot that seismic line into the orchard." Wasn't up to me, but he likes to bust my chops that way. Anyway, so this is just a cross-section interpretation to pull out the seismic data and also show some of the other relationships that we were looking at. The folding of the Pliocene Tulare Formation and an unconformity with some shallow Pleistocene material on it that I'll look at in a minute. But the point of showing you this is to emphasize that the deformation that's happening at the surface is a consequence of the growth of this fold and the up-dip propagation of the tip of this fault. As the fault propagates up dip, it's pushing this synformal hinge to the east into the basin. So this hinge is moving eastward as the fault propagates up, and it's rolling through and tilting up and deforming the shallow section that we can see. And I'll show you some examples of that, or at least an interpretation in a minute. So if we just to show you how this restores, this is unfolding it, just simple unfolding that folded section. And in our interpretation, there was some uplift and tilting of the older part of the section prior to the deposition of the Tulare Formation. The Tulare Formation cuts down section westward. And again, that I think is consistent with what we're seeing in this seismic line by Rob Sterling, that there is some older deformation, possibly in our case, We don't know if it's related to the West Tracy Fault, but there's some older deformation through here that is that's older and produced some tilting of the older section prior to the deposition of the Pliocene stuff. Okay, so what I want to do now is zoom in and take a look at some interesting stratigraphic relationships in the shallow part of the section. So what we're looking at is probably the upper 600 or 800 feet of the depth section. So this thinly bedded stuff that you can see in here is probably lacustrine sediments. It's related to when there was an inland lake within in the Central Valley in middle to late Pleistocene time. Okay, and you can see that these reflectors, you can carry them up through this synformal hinge and they're tilted and they come up here and they're part of this dipping panel above the tip of the fault. But if you look up, there's this blue marker that we've drawn into here where that separates the east dipping strata down here below from relatively flat lying deposits above. And you can see these relatively flat lying deposits and you can carry them across the synformal hinge and tie them into the flat lying section in the footwall of the fault out to the east. So let me just zoom in and take a look at the relationships right at the fold hinge in detail. So here are probably these older lacustrine sediments in the Tulare Formation that roll up through the hinge. And you can see this dipping panel here and they're overlain by relatively flat lying strata above this blue unconformity. This is an angular unconformity over here. And then the unconformity itself is folded right here above the tip of the fault, I should say, not above the tip of the fault, but up dip projection of the fault tip. So what's going on here? How do you explain or how do you account for the development of this angular unconformity here and its subsequent folding? Well, what we surmise is that the Tulare Formation was previously deformed and folded, but there was a regional erosional event, possibly due to sea level going down during one of the Pleistocene glaciations that cut an erosion surface across both the flat lying stuff out here and the tilted stuff here. And then the sea level came back up relatively rapidly. Again, what we are is we're right at the edge of where the tide line was, where this area was very susceptible to sea level changes. And so that unconformity was then subsequently buried rapidly. And then it was deformed by renewed or continuing growth and displacement on the West Tracy Fault, which uplifted and tilted and folded this stuff and basically folded that unconformity in a monocline as the tip of the fault propagated up into the northeast. So when we incorporate, put all this information together, the magnitude of the uplift of the basal Tulare unconformity, the width of this dip panel of the monocline above the fault, and the inference about how far to the east it migrated, and as well as the dip of the fault. When put this all together, we estimate that the slip rate on the fault to produce the relief that you see here on the Tulare Formation is on the order of about 0.2 to 0.3 millimeters per year of reverse slip on the West Tracy Fault. Okay, so it's probably somewhat higher than the Midland Fault. The rate of slip on this fault is higher than the slip rate on the Midland Fault. Certainly, it's higher than the rate of reverse separation on the Midland Fault. Okay, so that's where we see the West Tracy Fault right into here. How far does it continue to the west? Well, this dip panel, this panel of northeast dipping Tulare Formation, the Neroli, the Eocene, and the Cretaceous goes at least out to here. So I suspect that the fault probably goes at least out to here, maybe terminates against another structure here, maybe continues. But in any event, the length of this fault goes into the consideration of the magnitude that it's capable of producing. So before I wrap that part up, though, I want to show you one other piece of information. It's pretty cool. There's a series of geotechnical borings along Clifton Court Forebay that probably capture reverse separation or west side uplift of a Holocene stratigraphic marker. So all of the stratigraphic markers we looked at into here are pretty much middle to late Pleistocene. And the base of the Tulare that we've been using for our long-term average calculations of slip rate is Pliopleistocene. But if you look at what we're going to do is show you a series of correlated borings right into here that show you a reverse offset of the peat across the West Tracy Fault, the Holocene peat deposits. Okay, so here's the series of this transected borings. Okay, the base of the peat, the peat is this brown stuff, and it's sitting on top of silted clays that are blue. So here's the base of the peat on the west side of the West Tracy Fault. That same contact is down here. It's about 1.5 meters to 2 meters of difference between where it is on the upthrown side of the West Tracy Fault versus the footwall. And so that 1 meter to 2 meters of west side up displacement is consistent. And I should say that the age of this basal peat contact is probably about 6,000 years. So given the meter to 2 meters in about 6,000 years is equivalent to about 0.2 to 0.3 millimeter per year. So the long-term average slip rate that we're getting from the structural relief on the base of the Tulare Formation also seems to capture pretty well what the implied Holocene rate would be here. So we feel pretty good about 0.2 to 0.3 millimeters per year as a slip rate for the West Tracy Fault. So it's a quaternary active structure that passes beneath the southwestern part of Clifton Court Forebay. Seismic reflection and borehole data indicate that the fault tip is buried or blind beneath Clifton Court Forebay and off to the northwest. The co-seismic surface deformation is likely characterized by incremental uplift and folding, not by surface fault displacement, but by surface fold growth. So the surface deformation above this fault is going to be characterized by incremental folding rather than faulting. Based on the length of the fault, it's estimated to be capable of a magnitude 6.5 or larger earthquake based on its surface length and potential rupture area. As I said, our estimate is the long-term average reverse slip rate is about 0.2 to 0.3 millimeter per year. There's late Pleistocene fold growth, but also what appears to be possible 1 meter to 2 meters of offset of mid-Holocene peat deposits. So that's pretty good indication that this is an active fault. So to get back to this figure that I showed you earlier, this is a hazard curve showing the probability of multiple island failures occurring over a 25-year period. And so again, the purpose of what we're doing is to try to improve reduce the uncertainty and improve these hazard curves like these so that you can use them to ask the kinds of engineering questions that are important, like over the next 100 years, what is the likelihood that 20 or 30 island failures can occur simultaneously? And if you're really concerned for resiliency, maybe what you're more interested in is what's the likelihood that something like this could occur over a much longer period, 1,000 years, 2,000 years. Those are the kinds of questions you ask for very high consequence failure events for like nuclear power plants, LNG facilities, or something like this. Anyway, that's it. Any questions? Yes, sir. Okay, what is the question is, what is the recurrence interval? What is a potential recurrence interval for an earthquake on a fault that has a 0.2 to 0.3 millimeter per year slip rate. And what it depends on is the magnitude of the earthquake. Because if a magnitude, say magnitude 6.5 earthquake may accommodate about a 0.5 meter of slip, a magnitude 7 or 7.5 earthquake, maybe 2 meters of slip. So it takes 4 times as long to store up the strain for a 2 meter slip event as a 0.5 meter slip event. But just for the purposes of let's just say that the earthquake produces a meter of slip. So you're going to need something like on the order of 2,000 to 3,000 years to accumulate that much strain to release in an earthquake. And then you can scale it from there. So it would be twice as long for a 2 meter event, half as long for a 0.5 meter event. Very crudely. Yes, sir. Really? We your question, you said that there was Cretaceous offset on the Midland Fault, and you can restore almost all the in fact, you can restore all the displacement on the Tertiary without having any offset on the Cretaceous. So I'd say someone should show me data to demonstrate that. Okay. Okay. Okay, that's an excellent question. The question was, given that the Midland Fault is an early Tertiary fault, it has an early Tertiary history, it formed in early Tertiary. How can you use the length of the early Tertiary structure to estimate what the magnitude of an earthquake in the current tectonic setting? So that map I showed you is pretty much the length of the fault that's shown in red on there is where we're very confident that there's uplift of the hanging wall in late Cenozoic time. So at least that much of the fault has been active in late Cenozoic time. So that's the part that we place the highest confidence on, the highest in terms of the reach of the fault that could rupture in a single event. That's what we put the highest confidence on in developing a range of potential magnitudes on that fault. The way it's mapped as a whole series of left stepping on echelon splays going all the way up to some of those gas fields up in the northern part of the Delta. And some of those have some very interesting modest topographic relief associated with them, like Millar gas field and so on. But it doesn't look anything at all like the Montezuma Hills. So it's possible that the fault is linked up and has had longer ruptures. Hasn't been studied, so I'm really speculating here. But the magnitude of the displacement up to the north, if it's active up there to the north, is not the same as it is to the south. Therefore, ruptures are not always, they don't always break the entire length of the fault. So at a very rare event, if it breaks multiple splays heading up to the north, those kind of events may happen once every 100,000 years, for all I know. The more the lengths of fault that we have more confidence is where we see late Cenozoic structural relief. And that range of that length is about 25 to 30 kilometers. Yes, sir.
The Delta doesn't look like a very promising place to get vertical GPS data. Is there any hope for getting better data on these movements besides a bunch of bootleg borehole profiles?
Well, you take what you can get, but you can see thank you. The question is, is it possible to get better estimates of maybe geodetic? Your question mainly about geodesy? Yes. Yeah. Can you get reliable GPS velocities in the Delta? And I think the answer is yes. But what you have to do is you have to seat the GPS receiver way down into the Pleistocene where it's not, deflating or subsiding. It can be done, and that's been done in other places. I just don't know if it's been done in the Delta yet. Yes, sir.
Secondary question, it may not be a factor, but I think doesn't even need use of old gas fields as storage. So at certain times of the year, it's literally filling up the gas reservoirs for the winter, not only wastewater. Is there any kind of seismicity filling up?
Okay, so two questions. First of all, how common or how typical, say, were those events in October? Is that a fair? Okay, and then the other question is, what's the possibility that some of those that there's induced seismicity out in the area around the Delta? So the answer to the first question is that there are little events that pop off in there at a low background rate, and you can go and we pulled them up and taken a look at them. They're not anywhere near like at the rate out here in the East Bay or associated with some of the major San Andreas system faults, but there's a slow, steady rate of small background earthquakes in the Delta. They don't always line up along the Midland fault. Some of them are in and around the Montezuma Hills. So there is a finite but small rate of background seismicity in that area. So I don't know if you could say those are very typical or common, but they're not alone. There are other events like those little earthquakes in October. And then the other question is, what's the chances that some of that seismicity out there is induced? I would say there's a fair chance, because you're changing the all you have to do is change the shear stress inside of the in an area that's undergoing active strain, and you'll produce a change in earthquake rate. Yeah. Did you?
So in the almost 20 years since the 2005 study came out, they've been doing anything to help protect the levees that might fail and it's a place that could have happened anytime?
That's the question is, are they doing anything to remediate the levees? And I don't know. I do know that there were studies that were being done to assess how prone to liquefaction they were. But then I lost track of what any follow-up studies were. Does anybody actually, I'll throw the floor open. Does anybody else? Yeah. They have to repair these levees. There's not just earthquakes. There's rodents that are degrading them. There's all sorts of the study that I referred to, the Delta Risk Management Strategy study, looked at, in addition to earthquakes, other potential sources of levee failure. And so burrowing animals is one of them.
I was just gonna say that there are over 8,000 miles, almost over 1,000 miles of levees in the Delta that need attention. So it's not something that can happen in a few years, a decade, or maybe even.
It's triage. I think they're still trying to figure out because again, most of these levees, when they were built, they just piled stuff on top of the net. There's no documentation of what was done, what was built, did they throw some stuff on as part of the levee material? Do they throw stuff in there that could rot? So yes. That I don't know.
Jurisdiction of levee maintenance is extremely common. At least 15 different.
Thank you.
questions, maybe Jeff.